So this product rule then, used when two functions are multiplied together. For example, 3x times e to the 4x. What we do is we identify the two separate functions, and that's not always straightforward, but generally is. The two separate functions, and we call one of them u and one of them v, historically. That's a bit of a problem because if your handwriting is anything like mine, u's and v's can look very similar to each other. Let's look at the way it's written down here. On top of the fact that we've got u's and v's, we've also got y's. So y's and u's and v's, if your writing's a bit less than perfectly, you know, you're scribbling a bit, can all look the same. So if you're writing out this rule, which I want you to do, make sure it's saying dy by dx equals u dv by dx plus v du by dx. That's what the product rule says. Dy by dx equals u dv dx plus v du dx. And in words, it's that. We effectively multiply the first function by the differential of the second function and then add the second function multiplied by the differential of the first. So I often think about it like that when I'm actually applying it. I don't think of this, dy by dx equals u dv dx plus v du dx. I think of this. Multiply the first function by the differential of the second and add the second function multiplied by the differential of the first. So we do differentiate, we just differentiate each bit separately. So when we apply this product rule, we need to recognize that we've got these two separate functions, and I'm going to apply my same table of differentials, but I'm just going to differentiate each bit in turn and then plug them into this little rule here. That's the idea. If you look at your equation sheet or your data sheet I gave you for the exam, you've got this rule, so you don't need to remember it, but it's not a difficult one to remember anyway. So let's apply it to this. So you're going to need your little table of differentials. I'm going to do it in a way that you might want to adapt as a way to set it out, okay? So the first thing I would do would be identify which bit I'm going to call u and which bit I'm going to call v. So I sort of split the page into half, and you've seen this before if you've done this with me. So that bit I'm going to call u, and that bit I'm going to call v. Try and make sure your u's and v's look different. So whatever I've called u, I want to differentiate. What is the differential of u with respect to x? What is the differential of v with respect to x? So just take each function in turn, look at my table of differentials and differentiate it. Differential of 3x is just 3, and the differential of e to the 4x is 4e to the 4x. Just check you see that. If you're watching this video, just pause it and make sure you see the table, how that table helps you get that. Don't need that. Now I'll write down the rule, the product rule. It's always good practice to write down the rule that you're going to apply, because it's on your data sheet, so it'd be quite nice if it was actually on your work so you can use it and I can see you using it. U dv dx plus v du dx. Write down the product rule. Okay, so what's this rule telling me to do? It's saying that the differential of this whole function dy by dx equals u. That's 3x multiplied by the differential of v, which is 4e to the 4x. And then I'm going to add v, which is e to the 4x, and multiply that by du by dx, which is just 3. So literally I just write down what they are. So dy dx equals u, 3x, times dv dx, which is 4e to the 4x, plus v, which is e to the 4x, times du dx, which is 3. And then I use little rules of algebra to try and tidy this up. If I'm then going to go on and try and find turning points associated with this, in other words, let this equal 0, you'll make life a lot more easy for yourselves if you try and simplify this thing down. So if you look at it, 4 times 3, this means 3 times x times 4 times e to the 4x. So I can multiply the 3 and the 4 together to get 12. So that's 12x e to the 4x plus 3 e to the 4x. And now I'm going to think about factorising it. And if you remember algebraically what factorising means, it means look for common terms. And if I've got an exponential function, that doesn't change when I differentiate it. E to the 4x stays as e to the 4x. So that's bound to be common. And that will come out. E to the 4x comes out. And 3 is common to both. 3 goes into 3 once and 3 goes into 12 4 times. So I can actually take 3 e to the 4x outside a bracket and then think about what I'm left with. What have I got to times 3e to the 4x by to get 12x e to the 4x, 4x. What have I got to times 3e to the 4x by to get 3e to the 4x? 1, not 0, 1. 1 lot of 3e to the 4x is e to the 3e to the 4x. So I could simplify it like that. Well worth doing, because if you think about what's likely to come next, turning points in other words, if I want to find a turning point, that's when this equals 0. So I'm going to let this equal 0 probably. I won't write the 0 because it goes weird on the board. Equals 0. And if you remember what we said earlier, if the right hand side's 0 and I've got something multiplied, I can divide by it. I could divide both sides by 3e to the 4x and that would go. And I'd be just left with 4x plus 1 equals 0. So by factorising this, instead of letting that equal 0, I can actually make the equation I've got to try and solve much easier. So it's well worth simplifying and factorising definitely, because if I've got a factor that's common to both, that disappears when it equals 0. So there's an example of the use of the product rule. Just a quick recap. First step. Do I need the product rule? Yes, because I've got two separate functions multiplied together. What is the product rule? There it is. So I identify my u and my v, differentiate each one separately, and then plug them into the rule, and then simplify. Done. Okay?